Hello. This is the last as far as the explanation videos for the quantum physics section, and we're going to be looking at radioactive decay today. And firstly, we include an extra type of radioactive decay, the beta plus, which is basically a positron, a positive electron, and that is combined with the other types of radioactivity, our gamma radiation, our beta minus decay, and our alpha decay. Now with a beta plus decay, what basically happens is that a positive electron is expelled from a nucleus, and so what basically happens is that in the nucleus itself you have a proton, and it changes its form into this beta plus's positron plus a neutron plus a neutrino. And the reason for the neutrino, this was actually postulated before it was actually discovered, the neutrino, was that because this beta plus particle, the energy of it is not quantized. Now, in both the gamma and the alpha, it was found that the energy was quantized, and so it is postulated that there must be some other particle taking off the balance of the energy, and that's this neutrino, which was later discovered. The same with the beta minus, the regular electron decay. It also gives off a neutrino, but it gives off what we call the anti-neutrino. Now, we are going to go in, I'm going to actually show where these radioactive decay laws come from, and we'll discuss those in detail. We also discuss this formula looking at the relationship between the decay constant and the half-life. We'll go through all of those formulas shortly. So let me call up here. Let me bring up the data booklet. These are the four formulas that relate to radioactive decay from your data booklet. Now here we have got a sample, a number of atoms that are radioactive, and the N0 is the number of radioactive nuclei when t is equal to 0, when we start t seconds, when we start measuring. N is the number of those radioactive nuclei that are left over when we have gone a certain time. So when t is equal to some time, say t1, how many of those are left over? A is the activity. It's a number of radioactive occurrences per second or per unit time, and that is obviously equal to the rate at which these change, the rate of N change. Lambda is your radioactive decay constant, and this is the probability that a single nucleus will decay in a given amount of time. That is your decay constant. And T to the half is the symbol that we use for the half-life for that element. So we're going to actually go and we're going to prove these formulas now. I'm going to prove them for you. You don't need to know the proofs of them, but it's always good to know where things come from, so then you have a better understanding of them. So let me call up let's work on this document over here. I have my formulas here. Now, we have that dN by dt, the rate of change of the number of nuclei that have not decayed, is equal to minus lambda times n, the total number. This is the probability that this lambda is a probability, as we said before. The decay constant is a probability of a decay of a particular nuclei per unit of time. So when you multiply that by the total number that are there, that gives us the number that will actually decay in the unit time. Now, we do a little bit of mathematics with this, a little bit of algebra, and I hope you'll be able to follow this. If you need further help on it, please just come and see me. I'm going to prove some of these formulas here. So we can change this formula around to dn over n is equal to minus lambda dt. If we integrate both sides, this over here becomes the natural log of n is equal to minus lambda t plus a constant. Now one can see that if we viewed ln as y and t as x, this constant would be your y-intercept. And that would be when t is equal to 0. Now when t is equal to 0, n is equal to n0. So we can say that this constant is actually equal to ln of n0, because when this t over here is equal to 0, then ln is equal to ln n0. We have just started the process. So from that, we can say that ln of n minus ln of n0 is equal to minus lambda t. We can use our log laws to write this as ln of n over n0 is equal to minus lambda t. I can change this into my exponential form. So, sorry, not there. We're going to have n over n0 is equal to e to the lambda t, and I can change that formula around again to get my final form of the formula, that the number n is equal to n0e minus lambda t. And that's one of your crucial formulas that you have. Now, when we have, let me just take us a little bit further. If I take us down a bit further, there we are. Now, when we have the situation that t is equal to t to the half, so we're actually looking at t to the half, then we know that n is equal to n0 divided by 2, because that's the time, the half-life is the time taken for half the nuclei that were available to decay. So I can replace therefore my n by n0 over 2 when t is equal to the half-life, and I can put that into my equation here, and I can write that instead as t to the half. I can, obviously I've got an n0 on both sides, I can cancel that, so I get 1/2 is equal to e to the minus lambda t to the half. I can change this around. I can write this as 2 to the minus 1. I can put it into go from my exponential form into my log form, and that will be minus ln of 2 is equal to minus lambda t to the half. So we've got a minus and minus, we can make those both plus by multiplying through by a negative. And so we finally get our form of our equation that t to the half, the half-life, is equal to the ln, the natural log of 2, divided by the decay constant, which is a very convenient, nice formula to be able to use. So we have there our two formulas that we are going to use. If I go back up here, just bringing them back up. So we have that formula over there, and we have that formula over here. Now, A is equal to minus the change in n over the change in t. That's looking at my activity. That's pretty straightforward. And we also have our activity is equal to lambda, which is the probability that one nuclei will decay, times a number that will give us my activity. And I can substitute this into there, so I can get a formula for A. So I can get A, which is equal to lambda n, and I can put in my n is n0, so I'm going to get lambda n0 e to the minus lambda t, and I can add just a something on here, because this over here is actually equal to your activity at 0, because that would be the activity when you start off, when you have all the nuclei haven't decayed. So I could just write that as also as A0 e to the minus lambda t. Could write it like that. The data booklet writes it like this: lambda n0 e to the minus lambda t. And then obviously, so that's that formula, and then obviously this is a very important formula. So you have to be able to use these formula to solve problems. It's really important that you know your definitions, that you understand all these definitions over here. You need to learn these basically off by heart, especially all the starred ones. You need to be able to define. Good. Well, I hope you found that useful. And if you have any further questions, please come and ask me. Thank you very much.